Corba, Common Object Request Broker Architecture. We saw what is RMI already. We'll rush through RMI concept and see how Corba is better over RMI. RMI is basically the Java version of what is generally known as a remote procedure call, but with the ability to pass one or more objects along with the request. Coming to the Corba, it is a competing distributed systems technology which offers greater portability than RMI. Remember, we already know that RMI is the Java version of RPC, but Corba is not so. It is not tied to one language or single platform. It can be integrated with systems written in older languages as well as future languages that support for potential use in future. Corba services are described by an interface written in IDL, that is interface definition language. Ideal mappings are available to most popular languages like Ada, C, C++, Java, Lisp, Ruby, Smalltalk, COBOL, Python, etc. And also these mappings can be written for the languages that require Corba support in future. Under communication between Corba client and Corba services, method calls are passed to OPS, that is Object Request Broker. These OPS communicate via IAOP, that is Internet Interop Protocol.
Now we will see how a client and a server communicates. The client application first obtain object reference. The client acts as if it is invoking an operation on the object instance, but it is actually invoking on the ideal step which acts as proxy. Ideal compiler generates steps and skeletons passing through the step on the client side. The invocation continues through the orb. The orb examines the object reference and discovers that the target object is remote. It routes the invocation out over the network to the remote object orb. Then it will be passed to the POA, portable object adapter, and skeleton to get to the object where it is executed. Now here comes the terminologies in Corba. Corba object is a virtual entity capable of being located by an orb and having client requests invoked on it. Target object is the Corba object that is the target of that request. Client is an entity that invokes a request on a Corba object. Server is an application in which one or more Corba objects exist. Request is an invocation of an operation on a Corba object by a client. Object reference is a handle used to identify, locate, and address a Corba object. Servant is a programming language entity that implements one or more Corba objects. Now we will see what is actually inside Corba. Client. Client is a program entity that invoke an operation on an object implementation. Accessing the services of a remote object should be transparent to the calls. Interface repository. Registry fully qualified interface definitions, and it provides type information necessary to issue a request using the DII. Ideal step. It acts as a glue between the client and the orb. DII. Dynamic invocation interface. Allows a client to directly access the underlying request mechanisms provided by an orb, that is to dynamically issue requests to objects without requiring ideal interface, specific step to be linked in. The orb interface. It contains functionality that might required by clients and servers. The client orb core transmits the request to the orb core linked with the server application. The server orb core dispatches the request to the object adapter that created the target object. The DSI is the server side's analog to the client side DII. It allows an orb to deliver request to an object implementation that does not have compile time knowledge of the type of the object it is implementing. BOA, Basic Object Adapter. API used by the servers to register their object implementations. The object adapter further dispatches the request to the servant that is implementing the target object. Now the invocation can be done in two ways. We are going to discuss in first the static invocation. Static invocation. Client applications directly invokes operations on the client step. As we already know that The client steps are generated by ideal compilers, so the static interface are created and generated in the form of client step by the ideal compilers. Now the requests are passed through ORB to the server skeleton and finally to the server application. This type of invocation is recommended for applications that know beforehand the particulars of the operation they need to invoke. Advantages: it has better type checking, less runtime overhead, self-documentation. Now we will move on to the next type of invocation, dynamic invocation. Here, client dynamically builds request for the Corba object interface that has been stored in the interface repository. The remaining steps are the same as that of static invocation. There is no need for the server application to have special design to receive and handle request. It is generally used by dynamic client application where the nature of interaction is undefined. Advantages: servers can offer new services anytime without the need for recompilation on the client side. Now let us see the OMG's OMA. Object Management Architecture categorizes the objects into 4 categories. They are application objects, vertical Corba facilities, horizontal Corba facilities, and finally the Corba services. The application benefits in using OMA are: the first one is coding is quicker, hence applications can be deployed sooner. Second one is application designed around discrete services have better architecture. Thirdly, the robustness and scalability. The ORB, it is a central component of OMA. It provides all the communication infrastructure, for example, looking up and instantiating objects on remote machines, marshalling parameters from one application objects to others, handling security issues, and communicating with other ORBs using IIOP, which we will be discussing later. Next comes the Corba services. OMA defines a number of services useful for the application in general. These services range from indispensable naming services to higher level services such as transaction services. For example, some of the services are here. Lifecycle services. It offers facilities for creating, deleting, copying, moving Corba objects. Next, the naming service. It enables Corba object to register and be located by name. Naming context is used to set unique names. The next, security services. It provides the features such as identification and authentication, authorization and access control, security of communication, administering various security policies. The next comes horizontal Corba facilities. The facilities are useful across business domain. The 4 horizontal Corba facilities available are as follows: the printing facility, secure time facility, internationalization facility, and mobile agent facility. Finally, the vertical Corba facilities. These facilities are intended for unique requirements of specific markets. Some of the specifications available are imagery, information superhighways, manufacturing, and distributed simulation. Now we will see how Corba works in different networks. The Corba standard specifies a general inter-orb protocol for communicating between various Corba orbs and components. As the name itself says, it is a general protocol. It can be specialized. For example, for TCP/IP networks, it is called IIOP. For DCE, it is DCE-CIOP, that is Distributed Computing Environment Common Inter-Orb Protocol. Also, the SSLIOP, Secure Socket Layer Inter-Orb Protocol. This is for encryption and authentication. Then the HTIOP, Hypertext Interorb Protocol. This provides transparent proxy bypassing. If the applications are gonna communicate are present in different networks, for example, one in TCP/IP network and the other in DCE network, they can be communicated using the bridge. Now we will see how the interoperability issue comes into Corba. Ideal is a standard language. Remember, it is not procedural and it is used to define interface used by the Corba object. The ideal specification ensures the data is properly exchanged between dissimilar languages. It achieves this language independence through language mapping. The definition of the client interface to a remote object is placed in a file. This file is called the interface definition file. This ideal file is supplied to ideal compiler, and the compiler generates stubs and skeleton codes as well as some helper and holder files. For example, take IDLJ compiler, which translates ideal interface into Java interface and generates the class code for stub and skeleton and other helper and holder files. On the server side, the skeleton code is used to implement object method. It is used to start orb and wait for the request from client. The client uses the reference to the remote object and stub to call the method of that remote object. Now let us see how to create the ideal interface. The 4 steps are given below. Step 1. Define the remote interface. Step 2. Compile the remote interface. Step 3. Implement the server. And Step 4. Implement the client. Now let us see in detail. Defining the remote interface. The module name is first declared. The interface name is also declared, within which the methods are declared. Compiling the remote interface. The compiler command is given and the ideal file name here is hello.ideal. The compiler generates the following files, namely interface name poa.java, which is a stream-based server skeleton. Next, the interface name stub.java. It is a client stub. Interface name.java. This is a Java version of ideal interface. The helper and holder files are interface name help.java and interface name holder.java. Hello operations.java is a file which contains all the methods that have been shared by both stubs and the skeletons. Corba, Common Object Request Broker Architecture. We saw what is RMI already. We will rush through RMI concept and how Corba is better over RMI. RMI is basically the Java version of what is generally known as a remote procedure call, but with the ability to pass one or more objects along with the request. Coming to the Corba, it is a competing distributed systems technology which offers greater portability than RMI. Remember, we already know that RMI is Java version of RPC, but Corba is not so. It is not tied to one language or single platform. It can be integrated with systems written in older languages as well as future languages that support for potential use in future. Corba services are described by an interface written in Ideal. Ideal mappings are available to most languages like Ada, C, C++, Java, Lisp, Ruby, Smalltalk, COBOL, Python, etc. And also these language mappings can be written for the languages that require Corba support in future. Under communication between Corba client and Corba services, method calls are passed to orb. These orbs communicate via IIOP, Internet Inter-Orb Protocol. Let us see declaring the servant classes. First, we import the packages required for the server class. Hello.ape is a package containing the stubs. org.omg.cause_naming is used for naming services. org.omg.cause_naming context package contains the special exceptions thrown by the name service. org.omg.corba is a package that is the default one for all Corba applications. org.omg.portableserver and org.omg.portableserver.poa are the classes that are needed for the portable server inheritance model. Java util.properties is a package we need to initiate the orb. We define the servant object class outside servant.java class. We create a private variable orb. This value is used to invoke method. We declare and implement the required method. Now let us see how to build the client. Once the Corba ideal module is compiled, the client-side application can be developed that will request the services of the object. The client-side application is class that requires 3 packages. One generated by the IDLJ compiler and 2 Corba packages. The Corba packages are org.omg.cause_naming, org.omg.costNaming.namingContext package and org.omg.corba. Cost naming package contains the naming services used by the class to call Corba objects, and org.omg.corba. Package contains all the Corba classes. The following steps have to be followed. First is to create and initialize the org. Next is to get the root naming context. And next is narrowing down the object reference, which is a part of the interoperable naming service. And next is to resolve the object reference in naming. And the last is the invoking the operation. Next is to see how to build the server. The server-side program begins by importing the packages and creates an org object. 3 additional packages imported are org.omg.portableserver, .org.omg.portableserver.poa, and java.util.properties. The first 2 contains classes for portable server inheritance model, and the last package contains properties used to initiate the org. In the server side, the following steps have to be followed. First is to create and initialize the org, and next is to get a reference to the root POA and activate the POA manager. Next is the servant is registered with the org, then an object reference from the servant is got, followed by narrowing it to the proper types. And next is to obtain the initial naming context, and finally to narrow down the object reference. Next is to register the server with name server by binding the object reference in naming, and wait for the invocation. Now let us see the procedure to run the Corba application. First, open a command prompt and compile the ideal file. Then run the naming service. And next is open another command prompt and compile the server. And next run the server in the same window. The next step is open another command prompt and compile the client. And finally run the client in the same window.
Now let us see what is inside the ideal file. First we declared the module name. Here we declared it as matrimonial U, and then we declared the interface name, that is matrimony, and then we declared some of the functions. Now we'll see the implementation, that is the servant class. First we import all the packages needed. Then we create and initialize the org and set the org value. Then the database connection is given. Then we'll declare the methods and implement the methods in this section. We will move on with the client side code. First of all, we import all the packages that are needed for the client, and this is the coding part for the user interface we used. We'll create the org and initialize it, and then we'll get the root name context, and then we'll resolve the object reference in naming, and then we'll be invoking the operation. Now we'll move on with the server code. First of all, we import all the packages that are needed for the server. We'll create the org and initialize the org. We'll get the reference to the root POA and activate the POA manager. We'll create the servant and register it with the org. Next, we'll get the object reference from the servant, and then we'll get the root naming context. And then we use this naming context text, which is a part of interoperable. Next, we'll bind the object reference in naming, and then we'll wait for the invocations from the client. Lastly, now we'll see the procedure for running the application. First, we compile the ideal file using ideal compiler. Next,
we start the tname server. Once the tname server is ready, we'll open another window and compile the server file. We can run the server in the same window. Once the server is ready and waiting, we'll open another command window and compile the client. Now we can run the client in the same window. Now we have to open another window and compile the client. Now we'll run the client in the same window. Once the client is successfully run, the interface will come. Thank you.